Boom. Hello and welcome back to Calculus 1, section 5.4, working with integrals. So before we do any work, let's just go and review a little bit of integration and what we did so far. So in 4.9 we said antiderivative is going to undo the derivative. And we said we have to put plus c at the end of every integration because we are not able to retrieve the constant unless we have initial condition. So what I have is the working with integrals here. I have, so let's go first with integral of, let's say, x cubed dx. So if I have this, the answer would be x to the 4 over 4 plus c, and we are done. So that was in 4.9. Then we said, well, okay, I can have the same integral x cubed dx, but now I can have the integration go from 0 to 2. Now this creates a definite integral. Your integrand is still x to the 4 over 4, but now we are computing from 0 to 2, which gives you 2 to the 4 over 4 minus 0 to the 4 over 4 using the fundamental theorem of calculus part 1. 2 to the 4 is 16 divided by 4, and the answer is 4. So in this case, you are not getting a number. You're not getting a function. You are getting a number. And that number represents the area under the curve if the integral is completely above x-axis. So these are the two things that we distinguished so far. Now there are certain formulas that are there from the definite integrals that you guys should know. One of them is a linearity formula, which says that the integral of functions f plus g, right? You can do integration of each of these functions independently. Oh, and you can do that for subtraction as well, so plus minus. So you are allowed to separate integral into multiple integrals as long as the integrand has plus and minus inside, as long as it has terms. So each term can have its own integral. We also said that we can kick the constants outside. So if I have cf of x dx, I can kick constant outside and have just integral of f of x dx. We also said that the definite integrals, well, let's first take a look at some interesting concepts here. So integral of f of x dx, where you go from a to a, is 0. Now that should make sense because once you start computing, you will have f of a minus f of a, and that can only give you 0, right? So if the limits are the same, if you go from 3 to 3 or 7 to 7, the answer is 0. Now that should also conceptually make sense because definite integral compute area under the curve, and if you are going from 0 to 0 or 3 to 3 on the x-axis, then your width is 0, right? I don't care what your height is, it's multiplied by 0, so 0 times whatever number gives you 0 in the end. So this is one of the cool formulas. One formula that I did not mention, but it is going to be useful in our next section, 5.5, is the formula where you can interchange limits of integration. So you can put upper limit for lower limit. So you see, you have a standard setup A to B. And if you want to swap that from B to A, you just need this minus in front. So that should also make sense because when you compute the integral on the left, you will have capital F of B minus capital F of A. And if you compute the one on the right, you will have negative capital F of A minus capital F of B. And when you distribute the minus, you get the left side, right? This is actually useful, so this is a proof, if anyone was interested in a proof, but as a rule, you are allowed to switch order of integration. I'll give you an example which I'm going to erase, so because I don't want to ruin the flow of formulas over here. So if I have an integral from, let's say, 5 to 1 of, I don't know, x squared dx. You can swap that from integral to 1 to 5, x squared dx, as long as you put the minus sign in front. This situation will happen occasionally for our u substitution, which is 5, 5. So you need to know this rule. To swap the order of integration, to swap the limits in integration, you just put minus in front of the integral. All right. The last formula which we covered was that you are allowed to interrupt your integration at any point and then continue from the same point. So I said that integral a to b of f of x dx is equal to integral a to c f of x dx plus integral c to b of f of x dx. And the associated picture was something like this. This is your A, this is your B, and now this is the entire area. And then you are allowed to cut anywhere with C, and then when you compute A to C and you compute C to B, you get the combined area of everything. So you are allowed to cut within interval anywhere. So I'm just going to write over here that this C is between A and B. That has to be followed as a rule. So these are some formulas that are with us since we started integration on 4.9, and these are just general formulas. Now we're going to learn two formulas that might be very, very useful much later on in mathematics. I'm talking graduate school. So certain calculations in mathematics are very, very lengthy. Some integrals are very tricky and take very long time to solve. So if you know some of these tricks, you might be skipping a whole page of calculations. For instance, if you're looking for Fourier series coefficients, you have to do some integration, and then these formulas that I'm going to show in some problems cut out page or more calculations. So that's cool. So here are the formulas. So if f of x is odd function, then the integral negative a to a of f of x dx is equal to 0. There's nothing to compute. So we say if we are integrating odd function on a symmetric interval, the answer is 0. And I'll show that later. The second part over here, the second formula, if f of x is even, if f of x is even, then the integral from negative a to a of f of x dx is equal to two integrals from 0 to a from f of x dx. So it's much easier to compute your limits when limits are 0. Imagine if this a was, let's say, 5/3. Would you rather compute with negative 5/3 or 0? Well, hopefully you would rather compute with 0. So it's a time-saving thing, right, for you to use this. Now, if you don't remember the even and odd functions from your pre-Calculus 1, which is a year ago, the even and odd functions have the formulas. So let's go first with the odd function. Condition that needs to be satisfied is that f of negative x is the same as f of x. And for even, we have that negative f of x has to be the same as f of x. What are the odd functions? Odd functions are x to the 2n plus 1. So that means all of the polynomials that have only odd exponents. X cubed, x to the 5th, x to the 7th, x to the 9th. So those are odd functions. Also sine x, tangent x. So those are the all odd functions. Also cotangent is odd and cosecant is odd, but yeah. Now for even functions, you're generally looking at the even exponents and then cosine x and then secant x. Like those are the even functions that we generally run into. E to the x is neither. It's not even, it's not odd. All right? So ln as well. It's not even, it's not odd. So we have functions that are even, functions that are odd, and then we have functions that are none of the two, neither even nor odd. So this is these particular formulas are there, as I said, to improve quality of life. Remember that we did integration of sine, right? So I'm going to repeat integration of sine x dx, but instead of going from 0 to 2 pi, this time I'm going to go from negative pi to pi. And the answer is 0. But let's not jump into the answer because we memorized the formula. Let's actually solve this. So what do I have? Integral of sine is negative cosine x from negative pi to pi. This gives me negative cosine of pi minus negative cosine of negative pi. So now, cosine of pi is negative 1. So I have negative 1. Minus and minus gives me plus. And cosine of negative pi is the same as cosine of pi. That's the property of even functions. So now I have a 1 plus, and a cosine of negative pi is negative 1, and I get 0. Well, I could have just claimed that sine x is odd on the symmetric interval and write equal to 0 right away. So that's what, or integral negative pi to pi sine x dx is equal to 0 because sine x is odd function on the symmetric interval negative pi to pi. It is very important for all conditions to be satisfied, and all conditions means that you must have a symmetric interval. This does not work on asymmetric intervals. I know that x cubed is odd, but you can't claim this rule for x cubed going from 0 to 1. That's not a symmetric interval, so it's not going to give you 0 at the end. All right? Let's actually do that example to stress out this important thing. So if I have 0 to 1 of x cubed dx, we see that x cubed is the odd function, but if you put equal to 0, you will be wrong. Because we do get x to the 4 over 4 computed from 0 to 1, and the answer for that is 1/4. So why is it not 0? Because you went from 0 to 1. If you go negative 1 to 1 of x cubed dx, then yeah, answer is 0, because now we have symmetric interval negative 1 to 1. Before that, we did not have it. It was 0 to 1. That's not symmetric. So are we all clear on what the symmetric interval means? The number in the lower limit and the number on the upper limit have to be the same, except the one on the bottom is negative. Yes?
No, that's good. I just wanted to clarify.
Good. Well, we are done with those two formulas. The next formula that we are going to take a look is the average value of a function. So average value of the function is denoted by f with a bar on top, and it's going to be 1 over b minus a integral from a to b of f of x dx. So if the problem is asking, well, you have a word problem, let's say, and it's asking for averages, well, there you go, right? It's the average accumulation over whatever, some time or distance, whatever. You're just averaging. The idea of what this is achieving, there we go, is you have a function f of x, and this is calculating the value for the average. I'll call this value m or whatever. You know that this is a definite integral here, so it's going to give you this m that I have on the bottom. You know that the definite integral is going to return a number. B minus a is a number. 1 divided by that number is a number, so the whole thing is a number. So let's pick a problem from the homework to take a look at this concept of average. Beautiful problem. It says average height of a wave. This is problem 34 in the textbook. So average height of a wave. So waves are given by the formula with sines and cosines. So this particular wave has the formula y equals 5 times 1 plus cosine x on negative pi less than equal, x less than equal to pi. So what do I do? Well, I will do the average. That's 1 over, guys, these are your a and b, right? They can be given like that, or they can be given in the brackets like an interval, doesn't matter. So b minus a integral from negative pi to pi of 5, 1 plus cosine x dx. This is equal to 1 over 2 pi integral from negative pi to pi. Oh, kick the 5 outside. Sorry, I forgot to do that. You know that you can kick constants outside. So kick that outside, and all you have to integrate is 1 plus cosine x dx. Now, you know that you can do this term-wise, right? Do you also know that this is an even function? Cosine is even function, right? Yay! So we can actually use the quality of life formula from before to actually make this easier to calculate. So I will have 5 over 2 pi times 2 integral 0 to pi of 1 plus cosine x dx, and that's easier to compute. Now 2 and 2 will cancel on the outside, and you have 5 over pi Integral of 1 is x. Integral of cosine is sine x. Computed from 0 to pi. The whole thing is 5, but 5 over pi times pi plus sine pi minus big fat 0 for both, right? Because plug in 0 for x is 0 and sine of 0 is 0, so that's all zeros there. Now sine of pi is also 0. I don't know if you knew that one. Should. So we have 5 over pi times pi. Now they cancel, and you just get 5 at the end. So what's the average? Average is 5 for that wave. That's the average. Average height. The last concept in this lecture is the mean value theorem for integrals. Well, that was the average already. So what does the theorem say? Let f be a continuous function. Let f be continuous function on interval a to b. There exists a point C in AB such that f of C is equal to the average, which is 1 over b minus a, integral a to b f of x dx. Now, for the picture I had earlier, with the average, let's say, over here, for this point here, this is a C. For this point here, this is another C. So C1, C2, and so on. So how many you can have? I'm just going to leave it there. So let's compute the mean value theorem for this thing. I want to do 2 examples. Let's do, we already had the trig example, so let's use e to the x and the other one. We'll see. So let's go with the 36 first. So do the mean value theorem for f of x equals e to the x on 0, 2. So what do I have? Well, f of c is equal to the integral a to b. Oh, sorry, I forgot the 1 over b minus a, integral a to b, f of x dx. So f of c is equal to 1 over 2 minus 0, integral 0 to 2 of e to the x dx. 1/2. What's the integral of e to the x? Very good. Computed from 0 to 2. So it's going to be 1/2 e squared minus 1. You have to compute at 0. This is e to the x. E to the 0 is 1. So you have to compute that. Oh wait, why have the... I'm not supposed to have a bar on these. It's just the average of the function. Actually, what I should do is I should go average. No. Just C is equal to the average. There we go. Much better. So now, e to the c is equal to 1/2 e squared minus 1. And from here, you can compute c. You will ln both sides to get rid of the e, and you get that the c is equal to, and now you have ln of e squared minus 1 over 2. Now you can punch this in a calculator and get the exact value, not exact, approximate value, but we don't care. Exact answer is just fine. So what have I done? I set the mean value theorem part equal to the average, and then just solve the equation that I got at the end to come up with the value c. That value c is x, right? So those are these values, right? We got this value, or whatever, depending on the graph, obviously. Let's do one more example of this, and then, believe it or not, we're done. They're very short sections. So let's go with problem 40, because we can. The f of x is given as 1 over x on interval 1 to 4. So we start our f of c, which is the average, and that's 1 over 4 minus 1, integral 1 to 4 of 1 over x dx. This is 1/3. Does anyone know what is the integral of 1 over x? Beautiful. ln absolute x. Computed from 1 to 4. So you should always ask yourself which function, when differentiated, will give me 1 over x. And that is ln x. Because the derivative of ln x is 1 over x. Therefore, integral of 1 over x must be ln x. So we have 1/3. And then we have ln of 4 minus ln of 1. But ln of 1 is 0. So this is just 1/3 ln of 4. That's the answer. I hope this made sense. That's that. There's nothing else in the section. I hope you're not disappointed. So let's take a short break, and then we'll take a look at some other stuff.